This is the 19th video in our series on Lie algebras. And we're going to start off by fixing some notation and then recalling some important results that we'll use throughout today's video. Okay, so we're going to take L to be a finite dimensional semi-simple Lie algebra over C. That's in fact what we're going to take L to be for the next several videos. Then H is a Cartan subalgebra of L. Phi is the set of roots. And then L alpha is the root space for the root alpha. Let's recall that that's all x in L, such that if you bracket h with x, you get alpha evaluated at h times x for all h in the Cartan subalgebra. And then let's recall in the previous video, we proved that all of these root spaces were one-dimensional. So we could take the vector that spans this root space to be x alpha, and then we would write L alpha as, well, C x alpha. And then we had this root space decomposition, which was L equals H, direct sum with the direct sum of all these root spaces. We could write it either like this or like this using the fact that we have one-dimensional root spaces. And then let's also recall that for every root alpha, you could create an SL2 triple, which we'll call SL alpha. So in other words, there are these vectors H alpha in H, E alpha in L alpha, and then recall that F alpha was in L minus alpha, where those had the same bracket relations as the classical bracket relations for the basis of SL2. And that was a subalgebra of L. I guess that's important as well. So let's start with the following lemma. So it has two parts. This yellow part is that if we've got a non-zero vector in the Cartan subalgebra, then we can find a root so that if we evaluate that root at h, we get something that is non-zero. Okay, so how are we going to do this? Well, we're going to do this with the contrapositive. So in other words, we're going to suppose that we have something from h that gets mapped to 0 by all roots. In other words, let's suppose we have an h in h such that h is inside of the intersection of all of the kernels. So let's see, so something like that. But now let's observe that that is equivalent to saying that alpha evaluated at h is 0 for all alpha inside of the set of roots. Okay, nice. But now what are we going to do from here? So now let's take an x in L and then recall that x, well, or that L has this decomposition here. So it's as h direct sum with the direct sum over all of these roots of these one-dimensional root spaces. So that means we can write x as follows. We can write it as h prime. So that's the Cartan part of x, if you will. And then plus the sum over all of these roots of what I'll call C alpha times X alpha, where C alpha is just the appropriate complex number that makes this happen. Okay, nice. And now let's make the following observation. So let's take the bracket of h with x and see what we get. So that's going to be the bracket of h with h prime, and then plus the sum over all roots of, let's see, C alpha, and then the bracket of h with x alpha. So something like that. Okay, nice. But now, well, let's observe that the bracket of h with h prime is 0. That's because one of the parts of the definition of a Cartan subalgebra is that it is abelian. And then, well, let's also recall that we know what this is, given the fact that, well, x alpha is inside of this L alpha. So we can write this as alpha h times x alpha. But then, well, we constructed or we chose h so that this was always 0, this alpha h. Okay, so that means that this is equal to 0. Okay, but notice that that's occurring for all x in L. So in other words, what we have is that the bracket of h with x is equal to 0 for all x inside of L. But that's exactly what it takes for h to be inside of the center of L. But then let's recall that the center is a solvable ideal, and then the radical is the largest solvable ideal. It in fact contains all of the other solvable ideals. But then since L is a semi-simple Lie algebra, we know that its radical is 0. So let's see, that means that H is inside of the 0 vector subspace, which means that H is equal to 0. But, starting over here and ending right here is exactly the contrapositive of the statement we wanted to prove. Okay, so now let's move on to this pink dot statement. Okay, so now moving on to the pink dot, we want to show that H star, the dual space for H, is in fact spanned by all of the roots. Okay, so let's maybe set W equal to the span of all of the roots, which at the moment is simply a vector subspace of H star. And then we want to consider something called the annihilator of W, which is W with this superscript of a circle. That's the standard notation here. So that's going to be all H inside of H, so that theta evaluated at H is equal to 0 for all theta inside of W. Now let's make sure this makes sense. So if theta is inside of W, then it is also inside of H star, given that that is a subspace of H star. But H star is the dual space of H. That means it's the set of functionals from H to C. Well, I guess that's the definition of a functional, so it makes sense for theta to evaluate at H. Okay, nice. Okay, but then let's notice the following. But if we have an H inside of the annihilator, then that means that alpha evaluated at H is equal to 0 for all alpha inside of the set of roots. That's just like picking the correct theta up here. Oh, but then let's recall that if alpha evaluated at H was 0 for all alpha in the set of roots, then that means that H was 0. So anyway, that means that H is 0. But notice that what we've just shown here is that the annihilator is a subspace of the 0 subspace. In other words, this annihilator must be equal to the 0 subspace. Okay, but then now how are we going to finish this off? Well, it's going to be with a general fact involving like just linear algebra. And I'm not going to prove this. You guys can look up the proof of this if you would like to. And that says the following. If you take H star and you mod it out with W, and then you star that, you end up with a vector space that's isomorphic to the annihilator of W. So this is in fact if you put any vector space on top here, but in our setting, the vector space on top is H star. Oh, but then we said that the annihilator of W was 0. But what that means is that the dimension of H star mod W is 0. In other words, the dimension of H star and the dimension of W are the same. But since we're in a finite dimensional world, what that tells us is that H star must be equal to W because W is already a subspace. So just to reiterate, it's a subspace with the same dimension of the original space, which tells us that it is in fact the original space. Okay, so that's done with this proof. Now let's move on to the next step. Our next result revolves around a relationship between H alpha and T alpha. Let's recall that H alpha was, well, it's the special Cartan part of our subalgebra that's isomorphic to SL2 built out of our root alpha. And then T alpha was the unique element of H, so that if we took kappa of T alpha with little h, we got alpha evaluated at little h for all h in h. So we defined this T alpha in a previous video. And so, like I said, now we're going to have some sort of relation between these two. So the first thing that we'll prove is that H alpha is kappa of E alpha, F alpha, T alpha, or also 2 over kappa T alpha, T alpha, T alpha. Let's recall that kappa was the killing form. Okay, so how might we do this yellow dot before moving on to the pink dot? So previously we had the following. So for all x in L alpha and y in L minus alpha, we had, let's see, the bracket of x with y was equal to kappa xy T alpha. So like I said, that's something we proved maybe 2 videos ago. So now let's do this with x equal to E alpha and y equal to F alpha. And let's see what that'll give us. So we'll have E alpha F alpha is in fact equal to kappa of E alpha F alpha T alpha. But then we know something about the bracket relations of E alpha and F alpha, given that they form an SL2 triple and they're the standard basis here. This is H alpha. Okay, nice. So that's in fact this first equality right here. Okay, so now let's move on to getting the second equality, or really like equality from this H alpha and then that 2 over kappa T alpha thing. Okay, so also we know that 2 is the same thing as alpha applied to H alpha. And well, you might say, well, how do we know that? And that's because if we do the bracket of H alpha with E alpha, on the one hand, we know that that should be 2E alpha because we're inside of an SL2 triple. But then on the other hand, because E alpha is in the root space L alpha, we know that should be alpha applied to H alpha E alpha. And then just equating coefficients, we see that this H alpha or alpha H alpha must be equal to 2. So let's hold on to that because we're going to use that, you know, several times in this video, I believe. Okay, nice. But then let's notice that this alpha H alpha can be decomposed using this unique definition of T alpha to kappa T alpha H alpha. Okay, great. But from here, what we'll do is simply plug in what we got right above into this equation. So that's going to give us kappa of T alpha and kappa E alpha F alpha T alpha. But then the inside kappa E alpha F alpha is just a constant, and then this is a bilinear form, so we can bring that out of the outer kappa, and we'll have kappa of E alpha F alpha, kappa of T alpha T alpha. Okay, nice. But then, well, let's observe that we can use that to solve for kappa T alpha, or kappa E alpha F alpha in terms of the other one, just kind of depending on how we want to do it. So just to reiterate, that's from this like extreme left-hand side to the extreme right-hand side. So in other words, we'll have kappa E alpha F alpha is equal to 2 over kappa T alpha T alpha. Great. And now what we'll simply do from here is take this equation that we've just built and plug it into our original calculation and observe that brings us exactly where we wanted to be for this extension of this yellow dot equation. Okay, great. Now let's move on to the pink equation. Okay, so now for this pink equation, we'll take kappa of H alpha with itself. And then what we'll do from there is simply plug in the version of H alpha described by this like rightmost part of our equation. So that'll give us a kappa of 2T alpha over kappa T alpha, T alpha, and then another 2 T alpha over a kappa T alpha, T alpha. Great, but now we can factor the constants out of the first term and the last term, well, really the first entry and the last entry, and that'll leave us with 4 kappa T alpha squared times kappa of T alpha T alpha. Great, so something like that. But now it's pretty straightforward. You just cancel this thing in the numerator and then this squared in the denominator, and then you can multiply through by this kappa T alpha, and you'll have that pink dot equation. Okay, so let's look at a corollary of this lemma. So the corollary that we'll look at says that if we've got roots alpha and beta, then kappa, the killing form of h alpha, h beta, is always integral. And then kappa of T alpha, T beta is always rational. Okay, so let's see how we can get at that. So we're actually going to use the definition of kappa here as the trace of the composition of the two adjoint operators. So let's take x inside of L, which has the decomposition that we wrote before. So it's this decomposition where you have a Cartan part and then a sum over all of these root parts. So in other words, we should be able to write x as h plus the sum over all roots of c alpha x alpha. So something like that. And now we're going to look at add, let's see, h alpha composed with add h beta applied to x. But observe that that's simply the bracket of h alpha with the bracket of h beta with x. Great. But now, well, what are we going to get for that? Well, that's going to be the following. And actually, before we get to it, since we're using alpha and beta here, I'm going to rename this root to gamma because that's going to range over all of the roots. Okay, so let's see. We'll have h alpha, and then inside of that, we'll have the sum over all gamma, which are roots of, let's see, gamma applied to h beta, and then x, let's see, gamma. Let's see, those should be replaced with gammas given that we're like kind of re-indexing here. Okay, good. And then I forgot my bracket there. And then if you run this through again, you're going to get the sum over all gamma, which are roots again, of gamma of h alpha, gamma of h beta, x gamma. Okay, good. But now let's look at these gamma evaluated h alpha and h beta and observe that these are going to be eigenvalues of the bracket of h alpha with something and the bracket of h beta with something. But in a previous video, we proved that all of the eigenvalues of operations like that are integral. So all of these eigenvalues are integral. But then let's recall that the trace is simply the sum of the eigenvalues. But the trace of this operator is simply the killing form of h alpha, h beta. So if you sum a bunch of integers, you get an integer. Okay, great. So we've gotten this first part proven right here. And now how can you show that T alpha, T beta inside of the killing form is rational? Well, actually, this is pretty straightforward. And we can do that by replacing T alpha and T beta with this equation right here. So observe that kappa of T alpha, T beta is in fact equal to, let's see if we can get it right, is equal to kappa T alpha over 2 times kappa T beta over 2 times kappa of h alpha, h beta. So that's by reusing this like inner and outer part of the equation twice. You know, once for each entry inside of this killing form. Okay, good. And then next up, we'll replace kappa T alpha and T beta using this pink equation from our lemma, and observe that's going to give us 4, and then we'll have kappa of H alpha H beta over kappa of H alpha, and then kappa of H beta. But then we just showed that kappa of H alpha, H beta was always an integer. So here we have a quotient of integers. But a quotient of integers, well, that's exactly how you define the rational numbers. Okay, so now that we have this, let's see what we can do with it. Okay, so now that we know how the killing form acts with these T alphas, T betas, H alphas, and H betas, that means we can extend this to some sort of invariant bilinear form, well, symmetric invariant bilinear form on the roots, and kind of thus on H star. And we'll define it in terms of the roots like this. So we have roots alpha and beta, then the inner product, or I guess we haven't shown it's an inner product, but the bilinear form of alpha beta is kappa T alpha T beta. Okay, so again, that's how the thing is defined. Okay, so that leads us to the following observation. For all roots, alpha and beta, if you take beta and you apply it to H alpha, that part of the SL2 triple, you get 2, and then the bilinear form of beta with alpha over the bilinear form of alpha with itself. And what we're going to use here is this definition of T alpha here, but in this case it'll be with respect to T beta. Okay, so let's do this beta evaluated at H alpha, but now let's observe that that is simply kappa of T beta and then H alpha. Again, the way that T beta is defined. But now we can use our lemma to rewrite H alpha in terms of T alpha. And then, factor some stuff out as well. And that'll leave us with 2 kappa T beta T alpha over kappa T alpha T alpha. Again, I factored out the constant from the second entry. But then by the definition that we have down here, that's exactly 2 beta alpha over this alpha alpha, but that's exactly what we wanted. Okay, so now let's go on. Okay, so let's look at our next result. So we know that H star is spanned by the roots. So that means we can take a basis of roots. Let's take those basis of roots to be alpha 1 through alpha n. Then what we'll prove is that for all roots beta, there are rational numbers, Ci, so C1 through Cn, where beta is this rational combination of, the roots that we're using for our basis. The result here is that these are rational numbers and not just complex numbers. Because notice that if you're a root, so beta is a root, then that means that it's an H star. But since H star is spanned by that, it's actually the complex span of that. So again, the important fact here is that we get inside of the rational numbers for our C's. Okay, so how are we going to do this? So let's write beta as C1 alpha 1 all the way up to Cn alpha n, and this is with the Ci's complex numbers. And well, like I said, what we want to do is argue here that we actually have not just complex numbers, but we have rational numbers. Okay, so now let's do our bilinear form of beta with alpha I. And observe that that's going to give us C1 and then alpha 1 with alpha I all the way up to Cn and then alpha n with alpha I. And that's going to be true for all I between 1 and n. Okay, good. But now let's observe that this system of equations, if you will, is the same thing as a matrix equation. And what matrix equation is it? Well, it looks like this. Beta alpha 1 is the first entry of this vector over here. Beta alpha n is the last entry of this vector. And then over here, we're going to have a matrix made up of alpha 1, all the way up to alpha n, alpha 1, and then all the way down here to alpha 1, alpha n, and then all the way over here to alpha n, alpha n. And then over here, we're going to have our vector of constants C1 to Cn. Okay, good. But now, well, let's observe here that this matrix is a matrix of rational numbers. So it's in n by n Q, if you will. And maybe let's call this the matrix A. And then observe that this is a vector of rational numbers. So this is in Qn. Okay, but that means that we should be able to write this C1 through Cn as A inverse times this vector over here on the left. Okay, but now notice that if A is a matrix with only rational entries, then so is A inverse. Now, why does A inverse exist? Well, exactly because this is in an invariant bilinear form. And we know that because kappa was. Okay, so we've got a matrix with rational entries, a rational vector. If you take that product, you get a rational vector. So this is inside of Qn, but that means that each of these C's is a rational number as needed. Okay, so let's move on. Okay, so the next result may not look super interesting on its own, but it actually will allow us to arrive at some nice geometry between roots. And we'll see this via an example. So let's set E equal to the real span of alpha 1 through alpha n, where those alpha 1s and alpha n's, or alpha 1 through alpha n, were roots like we described on the last board. Then this like bilinear form on the roots can be extended to all of E, and it is in fact real valued, which we'll prove that, but that's denoted by the fact that we've got R over here, and it turns E into a real inner product space. So it's like a dot product, if you will. But then it being a real inner product space means that essentially it has the geometry of Rn. Okay, so what do we need for it to be a real inner product space? So by the definition of an inner product, we need, well, first of all, it to be inside of R. But let's recall that we immediately know that if you do this inner product of theta and phi, you will get inside of R, and that's because theta and phi are in the real span of those things. And we know that alpha I with alpha j is a rational number by this down here. So, well, that means you're going to get a real number in the end. I think that's pretty obvious. And then after that, you're going to need three more things, too, that are kind of free. So you're going to need that this is symmetric, and then you're going to need that this is bilinear. But like I said, those are free because the symmetry and the bilinearity doesn't matter if you do the span over R or over C. And we know it's symmetric and bilinear over C because it's built out of this killing form down here. So I'll just put here, this is a check, and that's because it's inherited from the original construction here. So what we need after that is for this to be positive definite. So this is something that you don't have for complex inner product spaces because you don't have this idea of positive and negative numbers the same way that you do in real inner product spaces. Okay, so let's see how we can do this. A theta inside of E, and we're going to do the inner product. I shouldn't say inner product yet, but we're going to do the form of theta with itself. But notice that is kappa of t theta with t theta, as described before. But then, mimicking what we saw in the previous proof, we know exactly what this is. And this is the sum over all roots theta of alpha evaluated at t alpha squared. But then by the definition of t alpha, that's going to be the same thing as the sum over all alpha in phi of kappa of t alpha with t theta squared. But then that's going to be the sum over all roots of, we have this alpha theta squared here. But then We already talked that that's always going to be a real number, so that's the sum of squares of real numbers, but that means that it must be bigger than or equal to 0. So that's one part of it being positive definite. The other part of it being positive definite is only being able to achieve 0 if you started off with 0. So let's look at that. So if you do theta with itself and you get 0, then, well, what do we have? Well, just going way up here to this stage, that means that alpha applied to t theta equals 0 for all alpha in phi. But then if something gets mapped to 0 by all roots, well, then that something originally had to be 0. That was like the first result of the day. So in other words, we have t theta is equal to 0, which means in turn that theta is equal to 0. But that finishes off this positive definite version of our proof. Okay, so now let's move on to an example where we see how this proposition is very nice. Okay, so here's a really nice example. Let's take SL3 with roots plus minus alpha 1 plus minus alpha 2 and plus minus alpha 1 plus alpha 2. So sometimes alpha 1 and alpha 2 are called simple roots, just by the way. And then let's set E to be equal to the real span of alpha 1 and alpha 2. But then that's going to give us a copy of the real plane, and then where the dot product is replaced with that inner product that we defined before. And then furthermore, we know the following thing from a result today. And that is that if you have T alpha, then that's the same thing as H alpha over kappa E alpha with F alpha. And furthermore, we know that alpha beta is equal to kappa T alpha T beta. Okay. So again, that's some stuff that we did before. This last one is just a definition of that inner product on E. And then, well, this first one was the relationship between H alpha, the part of the SL2 triple, and this T alpha. Okay, so now let's calculate some inner products of these simple roots. So let's do alpha 1 with itself. And this is actually going to be the same thing as we get if we do alpha 2 with itself. So by definition, that is the killing form applied to T alpha 1, T alpha 1. But then, using this first equation, that's the same thing as the killing form of H alpha 1 over the killing form of E alpha 1, F alpha 1 squared. Okay. But then we know what the killing form is on SL3. So let's recall that right here. And this is like kind of on SLN. So on SLN, the killing form of XY is simply 2 times N times the trace of X times Y. Okay, so let's use that here. So this is going to be 6, 2 times 3 times the trace of H alpha 1 times H alpha 1. But let's recall that H alpha 1 is the diagonal matrix with 1, negative 1, 0. So we have 2 copies of that. And that's going to be over, well, kappa of E alpha 1, F alpha 1 squared. But the 6 will square, giving us 36. And then we'll have the trace of, let's recall that E alpha 1 is 0, 1, 0, 0, 0, 0, 0, 0, 0. And then F alpha 1 is 0, 0, 0, then 1, 0, 0, 0, 0, 0. Great. And then, well, of course, we have to square that because that is squared in the denominator. But now let's observe that the 6 and the 36 will give us a 6 in the denominator. I think that's pretty clear. And then that trace in the numerator, after multiplying those two matrices out, is 2. And then after multiplying those matrices out in the denominator and squaring them, the trace will give us 1. So we get 2 over 6. In other words, we get 1 over 3. Okay, so we have alpha 1 with itself is a third. And then I should say here that also you can calculate very, very similarly that if you do alpha 2 with itself, you also get 1/3. And now, well, let's do the inner product of alpha 1 with alpha 2. Okay, so let's maybe say that is the next thing that we're going to do. So if you do, like I said, inner product of alpha 1 with alpha 2, then that's going to be the same thing as kappa of T alpha 1 with T alpha 2. But then replacing T alpha 1 and T alpha 2 with what we have up here, that's going to eventually be kappa of H alpha 1, H alpha 2 over, let's see, we have kappa of E alpha 1 with F alpha 1 and kappa of E alpha 2 with F alpha 2. Again, that's using this formula twice. Let's see what that's going to give us. That's going to give us 6 times the trace of the product of the two matrices that give us these two. So that's going to be 1, -1, 0, and then 0, 1, -1. And then over, well, the trace of each of those is 1, like we saw before, up here actually. So over 36. So notice that if you take the product here and then take the trace, you get -1. So you're going to have -6 over 36. In other words, you're going to have -1 over 6. Okay, but now let's find the angle between alpha 1 and alpha 2. So we'll do the cosine of what I'll just call theta sub alpha 1 alpha 2. So by a standard geometric formula, that's going to be equal to the quotient of this inner product of alpha 1 with alpha 2 over the square root of alpha 1 with itself times alpha 2 with itself. But after doing some calculation, you'll see that that is -1 over 6 over the square root of 1/3 times 1/3. In other words, that's going to be -1/2. Okay, so that's the cosine of the angle between those two simple roots, but that means that the angle between those two simple roots is equal to 2 pi over 3. And that brings us to the following very, very classic picture of the roots of SL3, which looks something like this. So let's say this is in the alpha 1 direction. So let's say alpha 1 goes here, and that's minus alpha 1. So those are those two roots. So the origin would like kind of obviously be right in the middle there. Then 2 pi over 3 is exactly 120 degrees. So that means that alpha 2 is like this. So there's alpha 2, and then down here is minus alpha 2. And then if you sum those, you'll get alpha 1 plus alpha 2, which kind of completes this up. So there's alpha 1 plus alpha 2, and here's minus alpha 1 minus alpha 2. And that's like a geometric picture of those roots, like in the copy of R2 built by E. Now I'll leave you with a couple of exercises. Okay, so here's a nice open-ended exercise, which can be done with everything that we've done so far without a ton of difficulty. And that is to classify all semi-simple Lie algebras of dimension 4, 5, 6, and 7. And I'll point out here that among these dimensions, either 1, 2, or 3 of the dimensions that we see here do not allow for semi-simple Lie algebras. So just be aware of that. And that's a good place to stop.